The Geostationary Operational Environmental Satellites, better known as GOES, is a joint NASA and NOAA venture to create the next generation of near real-time terrestrial and space weather monitoring system. Standing at 5.5 meters and weighing over 2,800 kilos without propellant, the GOES-R satellites carry 6 instruments that scan the Earth 5 times faster with 4 times the resolution than the previous generation of GOES satellites, producing data for critical government entities like the National Weather Service and SAR-SAT so they can provide life-saving services, including natural disaster tracking and search and rescue operations. In order to meet continuous monitoring requirements over the Western Hemisphere, 2 GOES satellites are stationed in geostationary orbit. GOES West primarily watches from Western CONUS to New Zealand, including Central America and the Pacific Ocean, while GOES East monitors North and South America, Western Africa, and the Atlantic. This configuration is imperative to maintain in order to track terrestrial weather systems across nearly the entire Western Hemisphere simultaneously, a feat that could not be achieved in LEO. The collected data is continuously downlinked to NOAA's Wallops Command and Data Acquisition Station in Virginia. It is then distributed to the National Weather Service to produce familiar radar images made publicly available on weather apps and the NWS website. The data is also delivered to the NOAA Space Weather Prediction Center to predict and track geomagnetic and radiation activity in Earth's space environment. Though GOES-R, which was renamed GOES-16 after launch, as is customary with the GOES program, is currently operating as GOES East. It is set to be replaced by GOES-19, formerly GOES-U, in April 2025. GOES-19 was launched on a Falcon Heavy earlier this year, and it is in its checkout phase as of the making of this video. GOES-18, which launched in 2022 on an Atlas V, replaced GOES-17 as the GOES West satellite in early 2023. While NASA and NOAA are the primary designers and operators of the GOES mission, Lockheed Martin and L3Harris served as the principal space system and ground system contractors. Lockheed Martin was also primarily responsible for spacecraft-level integration and environment testing. Many other government, academic, and commercial entities, including MIT and Lincoln Laboratory, were involved as subcontractors. GOES-R has 6 instruments on board, 2 for monitoring solar activity, 2 for observing the Earth, and 2 for characterizing its geo-orbit. Let's take a look at 3 of the fascinating instruments on board. The Solar Ultraviolet Imager replaces the earlier generation's Solar X-ray Imager to monitor the sun in the extreme ultraviolet. It operates in 6 bands UV ranging from 94 to 304 angstroms rendered on the right. SUV creates a full disk solar image to characterize active regions, solar flares, and indications of coronal mass ejections. These indications can help predict changes in solar activity and prepare for disruptive flares. The Geostationary Lightning Mapper in the GOES-R series is the first of its kind in GEO. It uses a single near-infrared detector to measure lightning activity throughout the Americas. At a 20-second product latency and an 8 megabits per second downlink, this data is used to forecast imminent cyclones and thunderstorms, often minutes before it is detectable via radar, and, in the future, can be used to produce historical data on Earth's lightning activity. The Advanced Baseline Imager is the main workhorse of GOES. Using 16 bands providing 0.5 to 2 kilometers of spatial resolution, this instrument provides near-constant spectral information of the Western Hemisphere in visible, near-infrared, and infrared channels. With 6 full-disk images and 12 CONUS images per hour, ABI's multi-channel imaging provides an array of data on weather, ocean, and hazards like fires and floods. This instrument provides a long list of benefits, including the data necessary to forecast weather, track storms, reduce emissions through monitoring, and reports on the effectiveness of agriculture and irrigation. As with any large-scale satellite system, the GOES-R series has faced challenges. GOES-R must be fully functional through the geo eclipse season, with a total outage time of just 3 hours per year. This requirement creates a tight power budget and stressing operational thermal environment. The Advanced Baseline Imager on GOES-17 was particularly stressed by these constraints once on orbit. The heat pipe on GOES-17's ABI was unable to operate at the design capacity, increasing the noise floor on the long-wave detectors due to thermal self-emission, which ultimately degraded imagery under some orbital conditions. The GOES-R team temporarily moved GOES-15 from orbital storage, while engineers redesigned the ABI thermal management system. Following the thermal redesign, GOES-17 was recovered to 98% of the design data capacity, while it waits to move to orbital storage upon the full checkout of GOES-18. GOES-R faced a ballooning budget from initial proposal, increasing from $3.6 billion to $11.2 billion, due in part to increased operational costs as scientists tried to redesign the thermal management systems for the ABI and the magnetometer once the satellite was on orbit. Despite GOES-R's challenges, 3 of the 4 satellites have successfully launched and are providing advanced Earth and space-based weather monitoring, with the last satellite, GOES-19, conducting on-orbit checkout in the winter of 2025. As Monica Coakley, PI of the MIT Lincoln Laboratory GOES team, notes, the success and technical achievements of the GOES-R program has been recognized by the government and public at large.